In this video, I'm going to go over classwork problems 12-1 to 6, which covers the fundamental counting principle. Basically, it's how likely is it that you could win the lottery? Are there enough cell phone numbers, etc. So, problem 12-1 says, Nick's new phone is prompting him to choose a 4-digit passcode. On the screen, it says, choose any digit 1 through 7. After typing in the first digit, the flashing dash prompts him for a second. As he thinks about his second choice, he wonders how many passcodes are possible. So, Nick's contemplating this problem. He asks himself how many decisions about the digits does he need to make. So he has to make 4 decisions, because he has to pick a digit for the first, second, third, and fourth. And then how many choices does he have for each digit? And then he has 7 choices each. Okay, Audrey is at her house working on this, and she wants to make a tree diagram. So she asks herself, how many branch points will it have, and how many branches at each point? So the tree would be really, really big and ugly when you're not doing that, but there would be, every time it would split into 7 different options, and it would do that at 4 different stages. So it's really ugly. Don't try to do it. So they text each other that they're stuck, and so they make what's called a decision chart. So the first digit, the second digit, third digit, and fourth digit. So there's the 4 decisions that they have to make in this decision chart. And so kind of ask yourself, how many options can he make for the first one? Well, he has between 1 and 7. Then how many options for the second one? He still has 7. He has 7 options here and 7 options here. So for each digit, he has 7 options because it says he can choose 1 through 7. It could be 1, 1, 1, 2, 2, 2, so they're allowed to be repeating digits. What you're going to do with these on a decision chart is multiply them. So 7 times 7 times 7 times 7, which is the same as 7 to the 4th power. So on your calculators, so there's 2,401 possible passcodes. So we want to know the probability that Nick's code is 2763. So there's only one of those out of 2,401 possibilities. Problem number 2 is very similar. It says, how many 4-digit number passcodes could you make using the digits 1 through 7 if you could not use any digit more than once? Make a decision chart, and then we'll look at the similarities and differences. So, first, second digit, third, and fourth digit. So for the first option, Nick still has 7 options for the first digit there. But he can't repeat it, so it doesn't matter what number he chose, he can't pick that number again. So now for his second digit, he only has 6 choices left. For his third digit, now he only has 5 choices left because he already chose 2 numbers. And then for his fourth digit, he only has 4 left because he chose 3 numbers already. And the same thing, you're going to multiply all of these, 7 times 6 times 5 times 4. So this way there's only 840 choices. So it's similar in the decision chart. They both have 4 digits. They both start with 7 options. If you're allowed to repeat numbers, then it stays 7 every time. If the numbers can't repeat, then it goes down by 1 because you take 1 out every time you pick one. Problem 12-3 wants you to kind of compare these situations. Can you repeat? Can you not repeat? Are they going down? Are they staying the same? So use a decision chart for each of these. Part A, a game contains 9 discs, each with one of the numbers 1, 2, 3, 4, 5, 6, 7, 8, or 9 on it. How many different 3-digit numbers can be formed by using any 3 discs? So we're choosing a 3-digit number. So we have first, second, and third. So we have these discs here, 1 through 9. So we have 9 options for the first one. Then we take one of our discs, and now we only have 8 left, and then 7 left. Again, we have these discs. You can think of them numbered like this. So say we chose a 3 for our first one. Now we would take it and put it right here. This is, again, just an example. Then we choose another one. Say we chose the 7. They can't repeat because we're putting the discs in these places. And then maybe the 2 last. Again, that was just an example, but it's 9 times 8 times 7. Or 504 different ways. For part B, it says a new lotto game called Quick Spin has 3 wheels, each with the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9 equally spaced around them. Each wheel is spun once, and the numbers and the arrows point to are recorded in order. How many 3-digit numbers are possible? So same idea. We have first, second, and third. So we're spinning 3 different wheels here. The first wheel has 1 through 9, 9 options. The second wheel has 1 through 9, 9 options. Third wheel has 1 through 9, also 9 options. So this would be 729. Again, they're similar and they both have 3 decisions to be made. They both have 9 options. This one stays at 9. This one goes down. You're not allowed to repeat. Repeating is okay. So this is no repeating. And this is repeating. Okay. Problem number 4 says Marcos is selecting classes for next year. He plans to take English, physics, government, pre-calculus, Spanish, and journalism. His school has a 6-period day, so he will have one of these classes each period. How many different schedules are possible and why? So think of these as his periods. First period, second period, third period, fourth period, fifth period, and sixth period. So he's taking 6 classes. For first period, it can be any of those 6 classes: English, physics, government, pre-calc, Spanish, or journalism. Let's say it's Spanish. Well, now there's only 5 classes left that he could take second period. Let's say it's journalism. That only leaves 4 classes, 3, 2, and so on. So there would be 720 there. For part B, how many schedules are possible if pre-calculus is first period? So same thing, first, second, third, fourth, fifth, and sixth. This tells us pre-calculus is first period. So first period only has 1 option. Maybe that's the only period it's offered. So now for second period, though, he still has 5 choices. Because pre-calculus is out, so then that leaves him 5 classes. Maybe he takes English here. Well, that leaves 4, 3, 2, and 1. So if you multiply all of these, there's 120 possible schedules. So for part C, it says, what is the probability that Marcos will get first period pre-calculus? Well, these 120 have pre-calculus first period out of 720 total possible schedules. So it's going to be 120 out of 720, which is 1/6. So he has a 1/6 chance of getting pre-calculus first period. If we think about this, right here, there were 6 options. One of those 6 was pre-calculus. And then part D says, what's the probability that he'll get first period pre-calculus and second period physics? So first, second, third, fourth, fifth, and sixth. Same idea. First period is pre-calculus, only one option. Second period is physics, only one option. Now he has 4 classes left to choose from here, 3 to choose from here, 2, and 1. So that gives us a total of 24 schedules that have pre-calculus first and physics second period. For problem number 5, it says, on your calculator, find a function labeled n with an exclamation mark or an exclamation mark. That's called the factorial button. On graphing calculators, it's in the menu probability. So I'll go over that in just a second. So calculate the value of 8 factorial. So what 8 factorial is, so actually I'm not going to tell you how to do that yet. So on the graphing calculators here, to get that, you hit math, go over to probability, and then you want this guy, number 4, it's the exclamation mark. I should have typed my 8 in first. So 8, math, probability, exclamation mark. So 8 factorial is 40,320. It also wants us to calculate 7 factorial, 6 factorial, 5, 4, 3, 2, and 1. So 7 math, exclamation mark, is 5,040. 6 factorial is 720. 5 factorial is 120. 4 factorial is 24. 3 factorial is 6. 2 factorial is 2. And 1 factorial is 1. For part B, it says which result is the same as the number of Marcos's possible schedules. So going back to problem number 4, he had 720 possible schedules. So this one, B, would be 6 factorial. So let me flip back here. So he had 720 possible schedules, which was 6 factorial. Look at how we got that number. 6 times 5 times 4 times 3 times 2 times 1. So 6 factorial is 720. So 6 factorial is the same as 6 times 5 times 4 times 3 times 2 times 1. And then part D, explain why 4 factorial gives the correct solution to the possible number of ways to arrange the letters M-A-T-H. So 4 factorial is 24. And if we think about the way to arrange the letters M-A-T-H, we have 4 options here. We could choose M-A-T or H. We take one of them. We only have 3 left. Take one more out. We only have 2 left, and then 1 left. 4 times 3 times 2 times 1 is 24. So that's what the factorial is. You multiply each of those whole numbers, counting down until you get to 1. So for problem number 6, remember this factorial button, again, multiplies all of these. 5 factorial is 5 times 4 times 3 times 2 times 1, etc. So it says simplify these without the factorial button on your calculator. So A is 10 factorial over 8 factorial. I'm going to write this out for this first one, and then we'll kind of see what that means. So 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Yep, let that focus. Okay. 10 factorial, 10 all the way down to 1. 8 factorial, 8 all the way down to 1. So by doing this, these can cross out. 8, 7, 6, 5, 4, 3, 2, 1. So 10 factorial divided by 8 factorial is just 10 times 9, or 90. Part B is 70 factorial over 68 factorial. No, we're not going to write all of this out. 70 factorial is 70 times 69 times 68 times 67 all the way down to 1. 68 factorial is 68 times 67 all the way down to 1. Same idea, 68, 67, everything in between down to the 1s is going to cross out. So we're left with 70 times 69, which would be 4,830. C is a little bit trickier. It switches it up a little. It's 7 factorial over 4 factorial, 3 factorial. So remember that explanation is a factorial. You multiply all the way down to 1. So 7 all the way to 1. Here we have 4 all the way to 1. And then 3 to 1. So this 4, 3, 2, 1 here can cross out with that 4, 3, 2, 1 here. You have a couple of options, so now we're left with 7 times 6 times 5 over 3 times 2 times 1. You can multiply and then simplify. You could simplify at the beginning. It doesn't make much of a difference. Our numerator becomes 210. Our denominator is 6, which gives us 35. And you might not even need this step. You might say, well, 3 times 2 times 1 is 6, which is going to cross out with that 6. So this one's a little bit longer, so $20 all the way down to 1. 18 all the way to 1. And then 12, 11, 10 all the way to 1 as well. So the 18 down to the 1 are going to cross out with that one. And so our numerator is 20 times 19. And our denominator would be 12 times 11 times 10 all the way to 1, which again we could simplify or multiply them up front. So this is 380 divided by 12 factorial. Is that a 12? Oh, sorry, I read the is it a 12 or a 2? I think it's supposed to be a 2. Over 12 factorial. Which gives you a really small number. But I think the problem is supposed to be over 2 factorial, which you would just do the same thing. Everything would cross out, and then you'd be left with the 2 and the 1 instead of 12 to 1 there. My book shows a 12, but my answer key shows a 2, so I'm not sure which way it should be. But either way, if it's this way, same thing. The 18s are going to cross out, so you're left with 20 times 19 over 2 times 1, which would give you 190.